Okay, so because now time is 10 o'clock, let's start. So, good morning, everyone. Thank you for coming to APCTP Colloquium today. So, the speaker of the day is Professor Eiichiro Komatsu, who is the director of Max Planck Institute for Astrophysics. And probably he is one of the most influential astronomers and cosmologists of our time. So, it is my great pleasure and honor to introduce Professor Eiichiro Komatsu for our APCTP Colloquium. So, Eiichiro, please start.
Okay, thank you very much. Welcome all. Today I'd like to talk about parity violation cosmology. That's fairly new subject in cosmology, and I wanted to share our excitement with everybody here. So let's begin. Our overarching theme is that we know the current standard cosmological model called flat lambda CDM requires new physics beyond standard model of elementary particles in field. In fact, specifically, if you look at this flat lambda CDM, flat lambda C, D, and M, each is new physics beyond standard model. For example, we don't know why the spatial geometry of the observable universe is flat, Euclidean. So there may be inflation or something else that we don't really know. Lambda is dark energy, cosmological constant. It may not be cosmological constant. C is cold, D is dark, M is matter. We don't know if it's cold. We don't know if it's dark. We don't know where the matter comes from. So the asymmetry between matter and antimatter, we don't know. There are lots of ideas. It has been 90 years since the first indication of dark matter. It has been 30 years since the first indication of dark energy. We still do not know what they are. So at some point, we start to wonder whether we missed something. And so I wanted to tell you that maybe we missed something that is the violation of parity symmetry. So this has been used a lot in the particle physics and also condensed matter physics. Cosmology is often behind both of the fields. We are finally bringing in this new piece of the puzzle. I wrote a review article on this subject a few years ago. It's available both arXiv and Nature Reviews Physics. Today's topic is parity symmetry. That's a new thing. But then this article also talks about cosmic microwave background and polarization of the cosmic microwave background. So if you are interested, please have a look. So I was told that I should dedicate the first 30 minutes to something that everybody knows. So this talk consists of two parts. First part is known physics. So you should all be relaxed, enjoy listening to something you know already. But this is actually quite important to set the stage for the new physics. That is the second part. So let's begin first. Parity. What is parity? Parity transformation is an inversion of all spatial coordinates. So x, y, z goes to minus x, minus y, minus z. Parity symmetry in physics states that the laws of physics are invariant under inversion of all spatial coordinates. Therefore, violation of parity symmetry simply means that the laws of physics are not invariant under the inversion of all spatial coordinates. So the question is, when we observe a certain phenomenon in nature, do we also observe its mirror image with equal probability? Sounds very innocent, But as it turns out, it's not so easy to actually really fully understand this. So let me try to give you an example. I guess if you're from East Asia, I don't have to explain what this game is, but because I'm living in Germany now, I have to explain the rules of the rule book of this game. The laws of physics underlines this game, right? So in this game, pitcher throws the ball, and hitter, that's actually me, we play baseball and also softball in this case, Sunday on the park in Munich. So let's begin. The pitcher throws, and I hit, then I run, right? And then I run to the first base, then I should run also to the second base, third base, and home base, and that's a score. Now, I'm going to flip one axis, so x-axis, then play it again. And the question is, can you tell whether this is the original image or this is the inverted image? So if you just rely on trajectory of the ball, it's Newtonian physics, right? Therefore, you can't really tell the difference between the original and the inverted image. Laws of Newtonian physics don't distinguish parities. And if you show this to European people, they really have no idea what went wrong. But probably many of you know that once I start running in the wrong direction, so this, right, then you know that this just cannot happen in nature. No matter how many times you play this game, this never happens. So this means that softball, baseball, the rules of this game will violate parity. So there's a definite handedness. You have to run in one direction, not the other direction. Yeah. Now, I'm not so familiar with football, or you call it soccer, and but I think if you see the movie of football played in original and parity inverted image, I don't think you can tell the difference. You can correct me if I'm too naive. Basketballs, volleyballs, I don't think you can tell the difference. Yeah? But for this game, you can. And in order to do so, you really have to know the underlying law of the game or physics. So parity and rotation are different things. And parity transformation, you have this transformation matrix whose determinant is -1. But if it's a rotation, it's 1. So for example, I ask you, okay, so you have the right hand, then let's invert all spatial coordinates, right? Now, can you do that only by the right hand? And the answer is no. No matter what you do by right hand only, that's rotation, not parity. To do parity, you really have to go to the left hand, yeah? The right to the left, that's the inversion of only one coordinate. You have to invert all coordinates. So you rotate your left hand by 180 degrees around the middle finger, like this. Then you accomplish the parity transformation. So this clearly tells you that parity symmetry is a statement about the symmetry between right hand and left-handed system. So let's talk about vector and pseudo-scalar, pseudo-vector, because that's a very important concept in this talk. Let's take a momentum, or let's take an electric field. And you have P here, P vector. As you might have learned in the class, physics class, nature doesn't care coordinates, right? It is only us humans would chart the space XYZ, and then decomposes the vector, which is a physical quantity, into the components of the vector, which is just human made, right? The electrons will move with certain momentum regardless of how we chart the universe, right? So this px, pi, pz are purely human-made things. Now I can transform my coordinates in different unit vector, the basis vector system, E prime. Then consequently, the components of the vector should change, p prime, px prime, pi prime, pz prime, but p are the same, right? So no matter what you chart the universe by your own coordinates, momentum doesn't care. Therefore, from this, you conclude that the components of a vector change sign on the parity. Now, if you take an angular momentum or a magnetic field, that's not, well, that transforms like a vector under rotation, but it doesn't transform like a vector under parity. Let me explain. Orbital angular momentum is r cross p. R, p, both are vectors. So if you take the product, each of these components changes sign. If you take the product, they don't change sign, right? Therefore, components of angular momentum, that is called axial vector or pseudo vector, don't change under parity. What this means is that if you wanted to probe parity symmetry in experiments, there's one thing you can do. And I think there's pretty much only one thing you can do. That is, you need to form a pseudo scatter out of your observables. Like a scatter, pseudo scatter is the invariant under rotation, but the pseudo scatter changes sign under parity transformation. So for example, you take particle A's momentum and particle B's angular momentum and take a dot product. This changes sign under parity. Now you observe these particles a million times, and then you measure these dot products a million times and take average. Because positive pseudoscalar becomes negative pseudoscalar after parity. If these phenomenon doesn't distinguish parity, then plus and minus must occur with equal probability. That is the name of the game. So you just make measurements of PA.LB, many of them, take the average, and that should be consistent with 0 within experimental uncertainty. And that's, of course, how it was done to discover parity violation in beta decay, the weak interaction. So 1956, T.D. Lee and Chen Yan, they noticed something. So namely, they read papers and try to see whether there's indication that weak interaction preserves parity. So they read papers and papers, and they notice that gravity, electromagnetism, and strong interaction preserve parity, but there's no indication that weak interaction preserves parity. Everybody assumed that weak interaction preserves parity, all fundamental forces will preserve parity, but there's no experimental evidence for it. So they suggested in this 1956 paper, well, let's test it. And here's a way. Then Madame Wu, so Chen-Xun Wu, took this idea, did an experiment, and showed that parity was violated. What did she use? She used pseudoscalar. So you have this cobalt-60, which has nuclear spin angular momentum pseudovector, J. And you apply magnetic field so that you know where this J is pointing at. Then you measure linear momenta of electrons that come out of beta decay. And you take the dot product and do measurements many times. And Wu found convincingly that E dot J average was not zero. It was actually negative. So this left image occurs in nature, the right never occurs in nature. So that's a clear violation of parity symmetry. World was shocked. So in fact, before Wu's experiment, when Wolfgang Pauli saw Li and Yang's theoretical paper before the measurements, he said, ich glaube aber nicht, dass der Herrgott ein schwacher Linkshänder ist. So basically, he was saying that this paper is nonsense. It cannot be that weak interaction violates parity. Okay? Why do you even bother? Then Wu showed convincingly that parity is violated. And then his answer was, how sure are we, right? Isn't it due to systematics? It was shocking. So everyone's prejudice fell apart. It's science. It's wonderful, right? It doesn't matter what you believe. You just have to make measurements. So in this talk, what I'm trying to ask is, does the universe, the cosmological scales, distinguish between left and right? And if you ask anyone in the field of cosmology research, they say no. Universe does not distinguish between left and right. That is probably true, but I just have to measure before I conclude. Taking a lesson from the history, that's always useful. So let's recap, right? Electromagnetism, you have our friends, physicist friends, Maxwell's equations. I always assume homogeneity in isotropy of space. So translation and rotation invariance. So these equations are invariant under Poincare transformation, so spatial translation and rotation and Lorentz boost. They are also invariant under parity transformation if you assume that electric field is a vector, magnetic field is a pseudovector, charge density is a scalar, and then charge current is a vector. So if you follow this logic, if there was ever magnetic monopole, then the magnetic monopole charge density has to be pseudoscalar. Okay, so all is good. Then, well, I mean, I was really happy that when I learned electromagnetism, Maxwell equations, I wasn't very happy because there's too many things to remember. Then I learned special relativity, very happy that now if somebody asks me to write Maxwell equations, I don't have to write 4, I can just write 2. So this divergence of F mu nu, anti-symmetric electromagnetic field strength tensor, that's first part of Maxwell equation. The second part uses something called dual tensor, which plays a prominent role in my talk. Okay, so let's recap. This anti-symmetric field strength tensor F mu nu is written like this. And for example, in a compact form, you can say F0i is electric field, Fij is magnetic field, but it has this Levi-Civita symbol, anti-symmetric symbol. Whenever you see something like this, you should think about parity, okay? So something about parity will happen when you see this Levi-Civita symbol. Dual tensor, as you might imagine, F0i dual would be magnetic field, and Fij dual will be electric field times Levi-Civita. Okay. Now, so this anti-symmetric field strength tensor, if you square it, then you have difference between magnetic field square and electric field square. This is a scalar quantity. It is invariant under rotation, and it is invariant under parity transformation. Dual. So let's talk about dual. Dual tensor has this 4-dimensional Levi-Civita symbol. Okay? As promised, F dual tilde, F tilde, 0i is magnetic field, and Fij tilde is electric field times Levi-Civita. Most importantly, FF dual is a pseudoscalar. It is invariant under rotation. It changes sign under parity. Yeah. So this is very important. Then let's talk about action principle. We're still talking about known physics, okay? So what is the action that gives rise to Maxwell's equations? So now you can be even happier, right? Now you don't have to remember two equations. You only have to remember one action. And then this F squared and A mu, J mu is A is a vector potential, four-dimensional vector potential. First component, this one is the electrostatic potential. And then A three-dimensional vector is a vector potential. F mu nu is an anti-symmetric tensor that comes out of this derivatives of A mu. And then so you can convince yourselves that because Fi0 is E, E vector should be derivative of electrostatic potential and A dot, and B is the curl of A. Yeah, and if you can convince yourselves that when three-dimensional vector potential is a vector, E is indeed a vector and B is indeed a pseudo vector. Yeah. So far, so good. And one set of Maxwell's equation comes from the definition. So it's called Bianchi identity. If you take the derivative of F mu tilde, it's zero automatically. Okay, that's very nice. The second part contains the source. So you just have to do the usual variation of the action and then stationary point. You find the stationary point, so variation should be zero. Then you get this Maxwell equation. That's nice. Okay. Then once you get this equation, you can derive electromagnetic waves. So you just take this equation, write it in terms of A mu instead of F mu nu, then you get this wonderful, you're going to get a wonderful equation. But before we do that, if you look at the action, that's like a treasure hunting. So this action is the invariant under spatial translation rotation, parity transformation, but it is also invariant under the gauge transformation. So if you shift A mu by derivative of a scalar, then and you assume that the charge current density is conserved. This is a continuity equation. Then this action remains invariant. Yeah, it's a treasure hunting. You have extra symmetry here. So in terms of the electrostatic potential and gauge potential, electrostatic potential can be shifted by the time derivative of F. This A vector can be shifted by the special derivative of F. Why do you want that? Because when you have this beautiful equation, Maxwell equation, you get something that looks like a wave equation for A mu, but not quite. You have this second term that you don't really want. So you can use this gauge symmetry to get rid of this term by demanding that your F that you can choose freely satisfies this box F. Box is this one, yeah? Second derivative of F is the divergence of A. If you do that, then indeed, divergence of A will be divergence of A minus divergence of A. Hence, you get, so divergence of A will be zero. So this will be zero. And you get very nice looking wave equation. Now, A mu had four components. We fixed F, so we reduced 1 degree of freedom, which leaves you with 3 degrees of freedom. But wait a minute, right? We all know that photons have helicity plus minus 1, so there are only 2 degrees of freedom, not 3. So what's happening? What's happening is that we haven't really fully exploited the gauge degrees of freedom of A, because you can still add F, which satisfies this box F equal to 0. So then specify F2 however you want. then you finally have 2 degrees of freedom. So a usual way people do this gauge fixing is to say electrostatic potential is 0, and then the divergence of A is 0. So this whole construction is called Coulomb gauge. This is consistent with Lorentz gauge because if phi dot plus divergence A is 0, so if phi is 0, it's 0. This is 0, so it's all consistent. So this means that this Coulomb gauge condition means that A is transverse. So the direction of A is perpendicular to the propagation direction of the photons. Everybody knows this, and we recover everything we know. That's wonderful. So now, so far, we talked about propagation of electromagnetic waves in static Minkowski spacetime. We didn't include expansion of space. But luckily, when you include expansion of space, you didn't have to change the equation. This stays the same, except you replace time with something called conformal time. When you have expanding space, this metric is no longer Minkowski. You have overall scale factor that stretches spatial dimension. Now, this the conformal time makes even time similar to this space component. So when you have defined this conformal time metric tensor in expanding space-time looks just like Minkowski times overall factor, time-dependent overall factor. So once you do that, the equation of motion remains exactly the same. That's nice. Good. Now, time for new physics. Most of people have never used FF dual in your life. Why? FF dual is a pseudoscalar. It's a rotation invariant. So you can totally put that into the action. Why haven't you seen it before? If you look at Landau and Lifshitz, classical field of fields, you see it. But Landau and Lifshitz also tell you that, well, by the way, obviously, they say always, FF dual is a total derivative. It is a total derivative of this vector. Yeah. Therefore, if you put this naively into the action, it's a surface time, which has no meaning. Now, new physics. Yeah. Instead of having FA dual into the action, we multiply that by a function that depends on space or time, or both. And this is no longer surface time. To convince you, let me say that you do integration by parts, then you get derivative of theta here in front. Yeah. I can even make this derivative of theta a generic 4-vector p mu, with p mu like derivative of theta. This term, not this, but this, and more precisely, this term with mu equals 0 is called Chern-Simons 3 form for Chern-Simons term. Chern and Simons are mathematicians. And this term has very, very interesting property. I think you are condensed matter physicist, you encounter this all the time. If you familiar with topology, you've seen this before a million times. It's very interesting. And then cosmologists, so however, this is not strictly speaking Chern-Simons term, but cosmologists are pretty sloppy in terms of terminology, notation. So we call this Chern-Simons. We even call this Chern-Simons after integration by parts. This is offensive to mathematicians, but hey, we're cosmologists, so that's okay. So we call this Chern-Simons term also. Now, is this funny thing? Is this exotic physics? No. This exists in standard model of particle physics. This term is responsible for decay of neutral pion into 2 photons. Okay? It's called ABJ anomaly, Adler, Bell, and Jakiv. This bell is the same bell of Bell's inequality. So this ABJ paper, this BJ, Bell, Jakiv, is the most highly cited paper by Bell that is not related to quantum entanglement. Yeah. So so this term, right, theta. So let's write this as theta is equal to pion divided by pion decay constant. We know what this decay constant is because we know that pions decay into 2 photons in 10 to minus 17 seconds. And this A, alpha here is essentially electromagnetic fine structures constant, 10 to minus 2. So we should all love this term. There's even more reason to love this term. As far as I know, this term has been rediscovered 4 times, at least 4 times in the past. 1969's ABJ anomaly. 1974, Chern-Simons 3 form, completely independently because Chern and Simons are mathematicians. This has to do with topology, okay? Wasn't thinking about physics. Then Jakiv noticed their paper, and then Jakiv started to explore this Chern-Simons gravity, okay? 2 plus 1. Very interesting. Then Taiwanese physicist Ni, he didn't know any of these papers, just out of consideration of equivalence principle, totally independent of pion or mathematics, he said this term should be there. And nowadays, people associate this term to axion. That's Sikivier's famous work in 1983. But no reference to any of these terms, any of these papers, right? So these 4 papers are essentially independent. But you know, when you look at this, these brilliant people discover this term 4 times independently. I mean, this term has to be there. And we know it is there because that's for pion. So all we are going to ask is, isn't it possible that this term exists for dark matter, dark energy, cosmic inflation, these 3 mysterious components in our standard cosmological model? Maybe this is what we missed for so many decades. Yeah. And I talked about this electromagnetic FF dual. It turns out that if you had any anti-symmetric rank 2 tensor, you can form FF dual of SU2 gauge fields, SUN gauge fields, non-abelian gauge fields, even 4 rank tensor. If you have anti-symmetric n rank tensor, you can form pseudo-scalar out of R dual, right? Well, whatever. Torsion dual. Non-metallicity dual, you name it. You got to love this. It's wonderful, right? So whenever you encounter anti-symmetric tensor in your project, think about forming a pseudo-scalar out of it, and you love parity violation. So new physics, parity violation, electromagnetism. We add this FF dual times theta into the action, and then vary, find a stationary point, and granted, you get this correction to the Maxwell equations. It has to come with derivative of theta, because if theta is constant, it's a total derivative. Yeah, everything is okay. Then the propagation of electromagnetic wave is also modified by this term. And it may not be obvious to you, but whenever you see this curve, right, this outer product here, it is sensitive to parity. So let me explain. Now, so in order to see parity, it's better to work with the eigenstates of parity. If you work with this Cartesian A, it's not obvious that this term has to do with parity. Okay, so we go to parity eigenstates, helicity. So we have this in Fourier space, x1 component of A, k, and x2 component of AK. You form this complex linear combination. This is the eigenstate of parity under rotation. So you have plus minus helicity state, and plus goes to minus under parity, minus goes to plus under parity. In this way, and then now I assume that for simplicity, theta has time independent, theta has space independent homogeneous expectation value, doesn't depend on x. Then your equation motion for propagation of electromagnetic waves depends on parity. You didn't have this before, okay? And previously, angular frequency of photons was equal to the wave vector. Now, it's not. All right. So what does it do to you? So let's say my dark energy or dark matter model is very simple. I have a neutral field, scalar field, spin zero. This can be composite, okay? So like pi can be a composite particle with net spin zero. That's okay. It's a good candidate for dark matter or dark energy, as I explain later. And then you have this harmless looking kinetic term, potential term, and then F square Maxwell term, and then now famous F dual. I write theta like pi, so chi over decay constant F. For pi F is 180 mega electron volt. We don't want dark matter or dark energy to decay into 2 photons in 10 to the minus 17 seconds. So F has to be much, much bigger than 180 mega electron volt. Okay? And chi can be composite, like I said, like pi. With chi can be fundamental scalar, like an axiom. Now, how do we distinguish between dark energy and dark matter? It has to do with this potential. So you have a potential, and then this field slowly rolls down. It doesn't yet oscillate. It slowly rolls down. In this case, pressure, time averaged pressure, is difference between kinetic term and potential. But this term is negligible compared to the potential. The time averaged energy density is a sum of the two terms, and this chi dot square is negligible. So you have a minus potential divided by potential, that's -1. When this W parameter equation of the state is -1, it's dark energy. It is slowly evolving. It makes the universe accelerate. If it is dark energy today, namely this mass, so essentially the field starts to oscillate when the Hubble expansion rate becomes comparable to the mass. If mass is very, very light, lighter than present day Hubble expansion rate, then in natural unit, this mass has to be lighter than 10 to the minus 33 electron volt. Then this field is still slowly rolling today. That's dark energy. If mass is greater than that, then field will be oscillating today. And that's dark matter. It doesn't have to be all of dark matter. It's sufficient. There is a fraction of dark matter. Then if you have that, okay, then your equation motion for electromagnetic waves was modified. This the omega squared, the angular frequency, is no longer equal to wave vector, wave number. You have this correction. And now, the photon frequency or photon wavelengths we're talking about is like centimeters. for cosmic microwave background. Centimeter is much, much smaller than the size of the observable universe. That's 10 gigaparsec. So for any circumstances today, this k square is much, much bigger than the second term. Then I divide omega by k to get the phase velocity of two circular polarization states, plus minus, so LHC plus, LHC minus. Then this phase velocity depends on the helicity states. So parity is violate. Then in this case, we can use WKB solution. Thus, this equation admits a plane wave solution like this. C plus minus in the initial amplitude. So if initially the photons were not circularly polarized, then C plus is equal to C minus. So let's say that's the case. No circular polarization at the beginning. This denominator depends on plus minus also. So if this difference between omega plus and omega minus was very significant, then you get circular polarization due to this term. But as I said, this term is tiny, okay? It's essentially 1 centimeter divided by 10 gigaparsec. So you can ignore this difference and put this, make this equal to 2k in a denominator. But you don't want to do that in the exponential, okay? Even tiny difference is important in exponential. So you keep this difference in the numerator, but not in the denominator, okay? Then you discover that due to the difference between phase velocities of right-handed and left-handed circular polarization states, linear polarization, that is a linear combination of circular and linear circular polarization states, left and right, linear polarization rotates, okay? So it doesn't generate circular polarization state, but when the initial photon was linearly polarized, as photons propagate, the plane of linear polarization of this photon rotates. And you can predict what that rotation is. You have to take the difference between omega plus and omega minus. That's why we didn't ignore the difference here, right? Even if it's tiny, it survives in difference. So difference is alpha chi time derivative, and you integrate over time, so you get boundary terms. So this rotation angle doesn't depend on whatever happening in the middle, but it's given by the field value today and field value at emission. So let's say you have some radio galaxy at redshift of 2, and then radio galaxy's synchrotron emission is polarized, so you have this linear polarization. But by the time we observe that linearly polarized light from the radio galaxy, plane of linear polarization is rotated. Similarly, for the cosmic micro background. So that's a preparation. Let's look at CMB. So cosmic micro background fills the entire universe, right? It's a fossil of the fireball universe, the Big Bang. Now, because we are observing sky from inside the Milky Way, we can't avoid to have this Milky Way in the middle. So let's go to the longer wavelengths. This is visible. With longer wavelengths, you always have our Milky Way in the middle, but by the time you go to microwave, it's full of light coming from the fireball universe, 2.7 Kelvin black body. When you then increase the contrast of your image, then you start seeing all these cosmic ripples, the fluctuations that existed at the beginning of the universe. And you still have this Milky Way in the middle. Yeah. So where did this light come from? If the Big Bang occurred from a single point, then light that was emitted from a single point was gone already. So that's not the light we're seeing. Entire space was lit up. If the light was emitted 1 light year away, and then that light is gone in 1 year, that's not the light we're seeing. The light we are seeing was emitted so far away. And this light came to us finally, right, after traveling 14 billion years. So that's the light we are seeing. Yeah? This light was emitted far, far, far away. Now, when it was emitted, it was last scattered by electrons far away. When light was scattered, it's polarized. And that polarized light will propagate to us and reach us after 14 billion years. So this is the cosmic micro background. So you can use this magic to remove the galactic plane in the middle. That's intensity anisotropies, not yet polarization. And polarization is like this. So every direction, CMB photon is polarized due to the scattering by electrons so far away. Okay. Now, the physics of CMB polarization is pretty simple. So let's say you have sunlight coming from above, you have the windshield of the car, the light is reflected by the car windshield, and it's horizontally polarized. Essentially, whenever you have incident light that's coming from one direction, that's scattered, then it's polarized. You can replace windshield by the ocean or swimming pool, then the light is polarized horizontally. You can also replace windshield by rainbow. Rainbow light is a scattered light of sunlight by the water vapor in the atmosphere that's polarized. Now, to prove it, you can buy polarized sunglasses from the company like Tarex. Then here you go. You can see through the car. Or you can get rid of rainbow, okay? So, for example, when you have the incident light that's coming from one direction, it's scattered by electron, it's polarized. Yep. But look, universe is isotropic. There's no up, there's no down, there's no left, there's no right. So when you have the same intensity of light coming from all directions, then scattered light is not polarized. However, the distribution of light around an electron can be locally anisotropic because there are fluctuations in the universe. We see it. So this distribution can be locally anisotropic. It is local quadrupole anisotropy. Hot, cold, cold. This kind of quadrupole anisotropy can be converted into the polarization. So polarization was generated and propagated toward us. We normally assume that plane of linear polarization did not change. But it might change by new physics, right? If the space is full of dark matter or dark energy fields, which are coupled to photons by Chern-Simons term, you'll be rotated by this angle beta. Maybe that's the way to prove dark matter and dark energy that we haven't done before. This effect is called cosmic birefringence because if you have a birefringent material like crystal, let's say sapphire, you shoot a laser light that's polarized into sapphire, then plane of linear polarization is rotated by birefringent nature of sapphire. So this effect is also not in physics, it's everyday physics, but we just apply to cosmology. So we did pseudoscalar, right? Remember, if you wanted to prove parity in the experiment, you have to have pseudoscalar. My pseudoscalar is EB correlation. So you have this pattern of CMB polarization. You can decompose that into eigenstates of parity. like vector and pseudo vector. You can decompose that into E mode and B mode. Then you repeat this experiment many times. Namely, you measure this EV from one region in the sky, another region, many regions. Then if average them, that's not zero, then that's a violation of parity in our universe. So that's the observed pattern of CMB polarization. And you decompose this is the eigenstates of parity, like that. Yeah. So these E modes and B modes have opposite parity. Then you so you have the Fourier vector of E and B modes. Squared amplitude of E, squared amplitude of B, E, B power spectra. These are actually scalars. These are rotationally invariant, and they are insensitive to parity symmetry. They don't care about parity. Similarly, temperature anisotropy, that's colored here, times E mode polarization, that's also scalar, not pseudoscalar. In general, you have 6 combinations: TT, TE, EE, BB, PB, and EB. 4 combinations are scalars. 2 combinations are pseudoscalars, and they are sensitive to parity violation. So if you're not familiar with this power spectrum, instead of, because sky is sphere, we decompose them into spherical harmonics instead of Fourier modes. And the x-axis is the multiple L. So it's essentially 1 nova wavelength. This leftmost part has wavelengths of fluctuation that's as big as the sky. And as we go to the right, higher multiples, wavelengths is smaller, shorter and shorter and shorter. So you start with this full sky map, you decompose them into spherical harmonics, and then compute the power at each wavelength. And that's the result, yeah? So this is the temperature power spectrum. This is E mode power spectrum. These oscillations prove that universe, when it was hot, behaved like a hot soup. It's a sound wave propagating in miso soup for Japanese, sundubu, jjigae in Korea. So these are essentially just sound waves propagating in the hot universe. In B mode, also measured. E mode is much bigger than B mode. But I bet most of you have not seen EB or TB. Almost all talks on cosmic micro background show you this plot, but never EB or TB. This is EB. This is the EB power spectrum measured from 2 space missions, WMAP and Planck. And if you compute chi-square, assuming that there's no signal, so chi-square relative to these data points, it's 126 for 72 degrees of freedom. It's terrible. So something is there. Can this be cosmic birefringence? So when you rotate the plane of linear polarization by angle beta, you don't generate new E or new B. You just mix them. You mix E and B. The E and B observed would be multiplied by this phase factor to E to the 2I beta. Then you just decompose them into E and B individually. You discover that E obs is a linear combination of E and B at the emission. And B obs is a linear combination also. Then you can compute E obs square, B obs square, EB obs square. Then you discover, right, that EB obs, BB obs, they're all linear combinations, and EE obs minus BB obs is EE minus BB at the emission times cosine, blah, blah, blah. So in the end, you discover that EB observed is a difference between EE observed and BB observed, if you assume that there was no EB at the beginning. All right. And luckily, we know that EE observed is much bigger than EBB observed, and we even know what they are. So all I have to do is to fit this that's observed to the EV observed and see if the fit is good. And it is excellent. So this now we have a chi-square of 65. Okay, wonderful fit. Now, but you have to be a bit careful because this rotation of linear polarization can be cosmological, so that's cosmic birefringence, or can be instrumental because of the imperfection of the instrument, it can rotate the plane of linear polarization by some degree. You have to correct it. So then after making that correction, you get 3.6 sigma significance for the preference of cosmic birefringence. You know, I'm old enough to know that 3.6 sigma can disappear. This was the best we could do using two space mission data, Dublin and Planck. I think it is fair to say that no one believed it because the implication will be significant, right? So, I mean, you have Chern-Simons term, maybe axiom, maybe whatever. So that was 2022. And we had to have independent experiments done by independent people using independent methodologies to determine instrumental miscalibration angle. That independent confirmation came in March this year. So this is Atacama Cosmology Telescope. That's ground-based experiment. And they modeled the instrumental miscalibration angle using optics model. Then they essentially saw the same thing. It's slightly less significant, but essentially we get two independent 3 sigma results. And because beta can be positive and negative, it is quite significant, in my opinion, that two independent measurements using different methodologies gave you the same sign. Yeah. So same sign for parity violation. Now, if you assume that the two measurements are independent, because one, right, measures mainly low multiples, the other one measures mainly high multiples, so they are nearly independent. Then we get 4.6 sigma hint of the cosmic birefringence. Well, that's interesting. So what are we worried about now? Essentially, we all used all of our knowledge. So Dublin and Planck, if there's something unknown about one of the channels of Planck instrument, maybe that's the reason, okay? Atacama Cosmology Telescope used a model for optics, but that's a model, not the real measurement of the miscalibration of the polarization instrument. So way forward is we need yet another independent measurement and calibrate angle using artificial polarization source. So you have some light source polarized, put it somewhere, observe that using your telescope the same way you observe CMB. In this way, you remove any ambiguity about the model inaccuracy of your optics or instrument. Yeah. So BICEP 3, Simons Observatory are doing exactly that. They are taking data already. We may have the final answer in a couple of years. So patience. Patience is good. Now, what is it, right? In the meantime, we can just think about what is it due to? If it is cosmological, what is it? So we know that if the light is propagating in a plasma that's magnetized, then plane of linear polarization can be rotated. That's Faraday rotation. It's well-known physics. This Faraday rotation, however, depends on the photon's frequency. So 1 over frequency square. We can test this. We can test it by parameterizing beta to be proportional to frequency to the nth power. N is -2 for Faraday rotation. We measured it. It's not -2. It's 0. It's -0.2 plus -0.4. We exclude Faraday rotation. Frequency independent beta is exactly what you expect from cosmic body fringes. This term doesn't depend on frequency. This F is the axion decay constant. Yeah. Alpha is fine structure constant. So this whole combination is 10⁻². So if you put 10⁻² here, then your conclusion is this coupling constant is electromagnetic fine structure constant. If this movement of dark matter or dark energy is comparable to decay constant. And that's essentially what you would expect from the simplest setup with no small fine-tuned values. In other words, if axion would ever give you this cosmological rotation, it would be 0.2 to 0.3 degrees. And that's exactly what we found. If it is due to dark energy, because this field has to be dynamical, this measurement rules out dark energy being cosmological constant. If you pay attention to cosmology, people are crazy about this possibility because the recent cosmological datasets, CMB, galaxy clustering measured from DESI collaboration, supernova data, they point toward dynamical dark energy. And our measurement is perfectly consistent with that. So maybe that's the explanation. Well, maybe it is dark matter. Then we know that at least a fraction of dark matter violates parity symmetry, and no one would be surprised because with interaction violates parity, why not dark matter violates parity also? So space may be filled with axion-like particles. That would be nice. Oh, these characters are Japan's manga characters. There's an author of the this manga, who had physics PhD, and so her name is Higson here. You can go to the website of Higson, and you can find this pretty manga characters of all elementary particles, photons, dark matter, Higgs, whatever, top, Potino, you name it. And this axion has Mexican hat potential. So it's really, it's very well done. So I'm very impressed. So this is free. You can use it in your presentations. I highly encourage to use that too. So let's switch the gear and talk about the very, very early universe. But same actions, same Chern-Simons term can give rise to parity violating circular gravitational waves, parity violating non-Gaussian density fluctuation. Really, really cool. So now we're talking about very, very early time. We're talking about before the propagation of photons in late time universe. Now we're talking about very, very early time. Okay. Inflation in nutshell. So more than 40 years of research in single slide. Inflation is accelerated expansion in the very early universe. Time derivative, second time derivative of scale factor is positive. Primordial fluctuations are generated quantum mechanically during inflation, and then they are stretched to larger scales by the action of the expansion. Density fluctuation, scalar mode, so the fluctuation in this scalar field is the origin of everything you see in the universe, stars, galaxies, planets, you, us, life. Tensor modes are gravitational waves, although we see gravitational waves from binary black holes and neutron stars, we haven't detected gravitational waves from early universe, yet to be discovered. Vector modes Magnetic fields from inflation, who knows? So this section, we're going to talk about something that you haven't thought about before. So cosmic inflation in a nutshell, you generate quantum mechanically in microscopic scales, these fluctuations, then it's stretched by exponential expansion to macroscopic scales. The size of the size of the atomic nuclei becomes the size of solar system in the tiny fraction of a second. That's inflation. Did it happen? My model of inflation is very simple. I have Einstein Hilbert action that will give you gravitational waves. I have scalar field equation that you have seen before that will give you scalar fluctuations. And I have this parity violating vector fields. So it's no longer a photon because photons didn't exist before electroweak phase function. During inflation, there's no photon. There's only maybe massless gauge fields. That will give you parity violating A. That will give you parity violating E dot B. That will give you parity violating E plus B. So generates this that will influence scalar and gravitational waves. And these are sourced contributions, right? These sourced contributions. People typically ignore right-hand side and worry about homogeneous equations, box Hij or box chi. Here, we're talking about sourced contributions here, okay? Now, as I said, photons didn't exist during inflation. So let's talk about new massless spin-1 particles, and they source scalar perturbations and gravitational waves. Notice that this comes with a product of E and B. If E and B were quantum mechanically generated, these are Gaussian variables. Square product of Gaussian is not Gaussian. So these spin-1 sources will generate Hij and chi, that's parity violating, and non-Gaussian. So this completely changes the basic prediction of inflation. It's completely new. So it's very interesting the way that inflation generates parity violation. Because inflation stretches wavelengths to macroscopic scales, you cannot use WKD approximations. Wavelengths changes like crazy. The rate of change of wavelengths is no longer small, it's huge. So therefore, if you look at this, and the second term now can exceed k squared. If it's a minus sign here, you get tachyonic instabilities. Omega squared becomes negative. So you have this exponential amplification of one of the helicity states. That's parity violation during inflation. And making prediction for this observable is not so easy. So many clever people did analytic calculations, but we are so lazy that we decided to just simulate it, okay? So put this into the computer, and then we ran world's first lattice simulation of inflation. So we can now calculate nonlinear evolution of this field due to this nonlinear term completely. No approximations. We can even use this to predict what the CMB sky looks like and what large scale structure looks like. So in a way, this is truly ab initio simulation of cosmic structure formation, because people doing structure formation simulation usually assume a Gaussian initial condition. Inflation never predicts Gaussian initial condition. It's non-Gaussian always. It's just that the non-Gaussianity is maybe small enough that you can ignore it, but not in this case. In this case, you have to have proper non-Gaussianity as an initial condition. So we simulate the universe from beginning to the end. So this is an exciting new research area. What about gravitational waves? So this is all you need, okay? You don't need anything else. And you get parity violating non-Gaussian contributions from U1 gauge fields. Then you get the power spectrum of gravitational waves. So now gravitational waves, helicity plus minus 2, not plus minus 1. And power spectrum of gravitational wave, helicity plus minus 2, is not the same. So plus 2 helicity has bigger amplitude than the minus 2 helicity state. This can be tested observationally. So I talked about CMB. CMB is sensitive to the wavelengths of gravitational wave. That's the size of the universe. So we call it attohertz, 10 to the minus 18 hertz. The pulsar timing array is sensitive to nanohertz gravitational wave. So about 1 year time scale. LISA, yet to be flown, is millihertz, and LIGO, Virgo, Kagura, Einstein Telescope, Cosmic Explorer, they are like, they're like 100 hertz, kilohertz. So now, if you have this source of contribution, you get this thing. So I guess what I want to say is, it's not just CMB. Inflation produces gravitational waves at all wavelengths, at least 21 orders of magnitude, right? And this one, blue line here, can be detected by any of these things. And this is circularly polarized. No astrophysical sources will produce circularly polarized stochastic background of gravitational waves. Only inflation. So this is a very clean probe of the early universe. If you discover stochastic background of gravitational waves that are circularly polarized, this is it. So let's look for it, okay? I think there's a very good physical motivation for it. So let's summarize. Let's find new physics. Parity violation is a new topic in cosmology. It may hold the answer to fundamental questions like, what is dark matter? What is dark energy? What powered the Big Bang? What is the physical origin of inflation? Parity is violated in weak interaction. No one will be surprised that the dark sector also violates parity. We have interesting hint, 4 sigma hint of cosmic birefringence. So if that's actually there, then maybe parity violation is everywhere. Gravitational waves. We recently wrote an article with postdocs in MPA about parity violation in shapes of galaxies. I think you just have to form a pseudo scalar, right? So you can, for example, take the dot product of spin angular momentum of spiral galaxies and velocity field. I think there are many, many possibilities, and I think this is getting quite exciting. So let me stop here and take questions. Thank you very much.
Okay, thank you, Eiichiro, for nice talk, and it was very impressive. So now the time is open for questions and comments, please.
Thank you. Can I ask?
Yes.
Yeah,
Yes.
well, yeah, very, very interesting talk. By the way, so about this new result of was it ACT? I mean, this
Yes.
birefringent. So yeah, it looks quite similar. Even this kind of has a best fit L dependence, very similar as well.
Yes.
Oh, so yeah, I mean, it would be nice if you just really, overlay these two graphs. But anyway, that's
Yeah,
really,
sure.
yeah. I mean,
So,
you just switch off one to the other. It's not so easy to see. But anyway,
yeah. So let me tell you, this best fit model is exactly the same because it comes from this.
I see. Also, essentially E minus B.
Yeah, it's identical. Only difference is over amplitude. Yeah.
I see. I see. Because that's how you feel it. Okay. No,
Yeah,
I see.
that's right.
All right. Okay. Anyway, well, very, very exciting. Yes.
Thank you.
Hello, can I ask a question?
Yes, please.
Could you show the second last slide?
Yes, yeah.
Yes. So around 10 to the minus 17 hertz, there
Yes.
is a kink or dip. The slope changes.
Ah, very nice. Yeah. Yes.
What's the reason for that?
Yes. Yeah. Thank you for the question. So the gravitational waves propagate into the universe, and then so inflation produces these gravitational waves whose wavelength is bigger than the size of the observable universe. But as the universe expands, these wavelengths enter into the observable universe, right? And after that, they redshift away. So they are sensitive to expansion history. These wavelengths enter the observable universe during radiation-dominated era. So when the energy density of universe is dominated by photons and neutrinos, here the wavelengths that enter the observable universe during matter-dominated era. And these epochs have different expansion history. And that change in expansion history is reflected in this change. So it's kink because of this huge log scale in the x-axis. But if you zoom in there, it's a smooth transition. But essentially, the reason is very simple. It's due to the change in the expansion laws due to the composition of the universe.
Okay, thank you very much. Then one more question.
Yeah.
What's the current status of light bird?
Thank you. Yes. So current status of Lightbird is next week, the September 25th, we're going to have the review by JAXA, so Japanese Space Agency. If they say they're happy with the mission, we're going to have another review in March next year. If they are still happy with us, they will go. So we're going to launch Lightbird in 2030s. So give and take 10 years from now. But these two reviews are very, very important to us. We have to pass these reviews in September and March. That's the status.
Thank you very much.
Thanks.
Sorry, Eiichiro, I have a question again. Yeah, about this sort of signals from parity violating, say, some infraton or whatever. So on those, say, high frequency where you usually use some like pulsar timing array or maybe a LISA or whatever. So is there any, how to say, or is it any proposal how to, say, detect this parity violation there?
Yeah, so I think the answer is no, but
not yet.
But let me explain why.
Yeah.
Why, right? So let's say we have, because way to detect circular polarization is not so easy. When you have the like a binary neutron star, you know where it is. Therefore, as Earth rotates, the orientation of this laser interferometer L shape relative to the source changes. Therefore, you can reconstruct all the polarizations of the source, including circular polarization. That's fine, right? But if you have a stochastic background, you can't do this because the signal comes from everywhere simultaneously. Therefore, you have to be able to measure all polarization, so all Stokes parameters of gravitational waves simultaneously. You just can't do it by having one L, right? So single LISA can't do it. You need to have two LISAs with slightly tilted configurations. So, and of course, you can't convince Lisa to launch 2 Lisas.
This Taiji,
Yes,
Chinese.
that's right.
Yes.
Yeah.
Yes.
So I don't know if there's anyone from Taichi or there's another mission, right? The Taichi was split from the original.
Tengen, yeah.
Yeah, that's right.
Yeah.
So because I think they are claiming that they can launch this mission simultaneously with Lisa, right? So if they can do
Right,
that,
but not both, perhaps.
that's right. One of them, yes, yeah.
Yeah, one of them.
So if Taizi or Tenmian was launched concurrent with Lisa, that would be very exciting, right? So,
I
but
see.
that's the only thing I know, and I
Mhm.
think isotropic stochastic background detected by SKA cannot probe circular polarization. I think it can probe circular polarization only for anisotropic part, like dipole and quadrupole. So this
Okay,
is
thank you.
more challenging, yeah. Mhm.
Right, it is. Yeah.
Yeah.
Can I ask a question? Hello?
Yeah, please.
Yeah. So for birefringence, you explained that the Faraday rotation cannot be the case because there is no frequency dependence.
Yeah.
But from the beginning, I mean, this photon or whatever Yuan masses field
Mhm.
has a high frequency, and there is a redshift to when you observe the CMB right now. So all the expressions are written in co-moving coordinates, and I'm curious, I mean, actually what is happening for that photon taking by refringence?
So very nice. The part that we talked about here, right, and the part we talk about here, they're physically distinct. They're not the same things. So birefringence refers to photons that were emitted at the surface of Russell scattering. This has nothing to do with the inflationary things. It's just, this is the physics of the energy scale less than 1 electron volt.
Yeah, but
So
still there is a redshift of 1,000, right?
That's right, yes.
So that is not reflected in frequency.
That's right, but you see this plane of linear polarization, right, is rotated. And no matter what wavelength is, you get the same rotation, right? So let's say at the surface of Russell scattering, you had photons that was 3,000 Kelvin. And today it's 3 Kelvins, right? So you go from optical to radio. They're rotated by the same amount, nonetheless, right? So it's not about the, it's about the rotational polarization as a function of frequency, not so much about amplitude of photons, right? So temperature changes, of course, but the polarization direction is independent of frequency.
Okay. And the other question is, when you simulate this E dot B term as a source,
Yes.
I know that this magnetogenesis is a huge, I mean, big problem in cosmology. And what is the assumption made here? And
yeah, so this E dot B is not electromagnetic E dot B. This is some weird massless spin-on particles that might have existed in the early universe. So these are not photons.
yeah,
These
but
are, yeah.
You just compute everything once the inflationary boundary condition is given, or you assume the boundary condition for that?
So we assume inflaton potential, let the inflation start. We solve this equation simultaneously with inflating background. Then essentially we're solving this equation, couple equation, right? We don't solve this. This just gives you the expanding background. We just solve this semi-consistently on the lattice. So you generate this parity violating A, that will back react to chi. And that's what's solved self-consistently. Yeah.
Okay. Thank you very much.
Yeah, thanks.
Okay, any other further questions or comments?
A very small question. Eiichiro, where are you
Yeah.
now?
Nagoya, I'm visiting
I
Nagoya
see,
University.
That's
yeah.
fine, because if it is Max Planck, then this will be really early in the morning. Huh?
That's right. Yeah, yeah.
Okay, sorry.
yeah, no problem.
I don't know if you can say in Munich it's early morning or deep in the night, probably 3 a.m. or something.
Yeah, it's 4:30 a.m. Yeah.
Okay, so you can anyway get up if you try.
That's right.
Oh, that's
Yes,
what Jinuk you do, huh? Sometimes.
Sometimes, yes. All right. So, is there any further questions or comments on Eiichiro's brilliant presentation today? Okay, so otherwise we enjoyed for almost 90 minutes. Very brilliant and illuminating presentation by Eiichiro. So let's thank Eiichiro again. Thank you very, very much.
Thank you.
Thank you very much.
Okay, so I hope you have enjoyed the presentation. So have a nice day.
Goodbye.
See you. Bye-bye.
Bye bye.